All right, so for the Vesper model stuff, when I taught you how to do this stuff, I taught you how to look at the valence electrons and know the bonding sites, okay? And the bonding sites determine how many bonds it has to make. So hydrogen, we know, had one valence electron, so it had 0 lone pairs and 1 bonding site. So it can only make single bonds. And then remember we talked about polarity, and non-polar is equal sharing of electrons. So a hydrogen bonded to a hydrogen, okay, would be non-polar because they're equally sharing those electrons. If you have a fluorine bonded to a hydrogen, fluorine is a lot more electronegative. So this is a polar molecule, okay? And then it's not a full-on charge. It's called a dipole-dipole interaction. So it means it has a pole, positive side and a negative side. So it's a slight positive charge and a slight negative charge. It's not like an ionic compound that is transferring electrons, where you have the sodium transferring an electron over to chlorine so that sodium becomes a full-on positive one, chlorine becomes a full-on negative one, and it makes a compound sodium chloride. All right, these are covalent molecules, so they are sharing electrons. They are not transferring like ionics.
How do we know if something is covalent or like ionic?
If the first element is a nonmetal, it's covalent. If the first element is a metal, it's ionic.
Okay, thank you.
Yep. So hydrogens and halogens will always make single bonds because they only have one bonding site. Oxygen's family has 2 lone pairs and 2 bonding sites, so it is going to make 2 bonds. There are 2 ways to make 2 bonds. You can either make 2 single bonds, and if you do that, because of the lone pairs, it pushes the geometry down, and the shape is called bent, and it looks like that. And a bent molecule is always polar. So it's going to be like OS or OF2 or SBR2 or SEI2 or H2O or something from oxygen's family bonded to 2 things, a hydrogens or halogens. Now, the other way to make 2 bonds is to make a double bond. This means it's sharing 2 pairs of electrons. Okay, so it has 2 sticks, and if it's oxygen bonded to oxygen, that's nonpolar. Oxygen bonded to something else, polar. And then remember, anything bent is always polar, even if it's the same thing, because of the lone pairs. Then, nitrogen's family has 5 valence electrons, so it has 1 lone pair and 3 bonding sites. So it has to make how many bonds? 3. So if it makes 3 single bonds, it's going to be trigonal pyramidal. And it's going to look like this, because the lone pair is on top, it pushes everything down. This is always polar, just like this is always polar because of that lone pair. It doesn't matter if it's all hydrogens next to it. Okay? It's always polar. Now, the other way to make 3 bonds is to have a double bond and a single bond. This would always be polar also, because it's 2 different elements bonded to it. And that's linear because it's, what do you call it? It's linear because of the double bond. And then the triple bond here is sharing 3 pairs of electrons. All right, if you share 3 pairs of electrons, it makes triple bonds. And then nitrogen to nitrogen is nonpolar, nitrogen to phosphorus, polar. All right, and then just remember, the single bonds are the longest but weakest. The double bonds are medium strength, medium length, and the triple bonds are the shortest but the strongest. So you definitely need to know that for your test on Monday. All right, then carbon has 4 bonding sites. So carbon has to make how many bonds? 4. So how can it make 4 bonds? Lots of ways. It can make 4 single bonds. That is called a tetrahedral. Okay? And that is non-polar if all of the same things around it. So if it's CF4, H4C, CBr4, SiI4, SiBr4. If it's 4 things bonded to carbon or silicon, whichever one's the middle atom, it's going to be non-polar. But if it was like F2Br2, then it would be polar because those are 2 different things bonded. They pull differently. Okay? And then it could also have a triple bond and a single bond. It's going to triple bond with nitrogen's family because it loves a triple bond to make it happy. And it's going to single bond with a hydrogen or halogen. It could make 2 double bonds. Well, what family is it going to double bond with? Oxygen's family. So technically, this one's non-polar because it has an equal oxygen on both sides pulling on it. Okay, so that's non-polar. This is polar because of the lone pairs on oxygen, and this is actually a trigonal planar, which is 120 degrees. It's a double bond and 2 single bonds. So those are the 4 ways that carbon can bond with 4 bonds. All right, and then boron's family has 3 bond sites with 0 lone pairs, so it technically doesn't need a full octet of electrons. It's okay with 6. So it's going to form trigonal planar, which is 120 degrees. And if all three things around it are the same thing, then it's nonpolar. But if I change this H right here and made that an F, that would make it polar because that F is going to pull differently than the H's. Okay? So it's really important to understand that because on your test, when it asks you, which of the following is a polar molecule, and it gives you BF3, CF4, OS, and N2, which one's polar? Non-polar planar, non-polar tetrahedral, polar linear, and non-polar linear. Okay, because it's two different nonmetals, polar. All right? Or they might give you something that says, which of the following is non-polar, and they give you, H2O, O, F2, B, Cl3, and NP. So which of the following is non-polar? That's bent, always polar. This is bent, always polar. This is linear, but two different things, so it's polar. That's trigonal planar, all the same thing, non-polar. Okay? And if they gave you NH3, that would also be polar because it's trigonal pyramidal, which is always polar. All right? So just stuff like that. That's how they ask questions like that. So you got to know, just practice that. You're going to practice it today. Now, the last thing we talked about, okay, and I just want to review real quick, is what if it's a bonding domain of 5? Okay? All of these, are 4, because a lone pair and a bonding site are both domains. So if it has 3 lone pairs and 1 bonding site, it's 4 domains. 1 domain, 4 domains, 4 domains, 4 domains, 3 domains. Okay? But what if it has 5? Well, there's 4 things that you have to know, and you just got to memorize them. Okay? The first one is called, the first one's called trigonal bipyramidal. Okay? So trigonal bipyramidal. And that's if you have something from nitrogen's family bonded 5 times. You say, well, I thought it could only bond 3 times because it has 3 bonds. This is if every electron in nitrogen is bonding. So these are, anytime you have 5 or over domains, it's an exception to a rule. So you have like H, 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 okay? So there's no lone pairs on it, all right? Because it's using all 5 of its electrons, and it's bonding like that. So you might have, NH5, you might have NF5, you might have PCl5, you might have ASI5. It's something from nitrogen's family bonded 5 times. That is your trigger to be like, oh, that's trigonal bipyramidal. Okay? Any question with that? Just nitrogen's family does it because it has to have 5 valence electrons because it cannot have any lone pairs on it. Okay, so nitrogen's family bonded 5 times gives you that. All right, so the next one is seesol. And seesol is going to be oxygen's family, so anything in oxygen's family, and it's going to be bonded 4 times. So we say OF4. All right. Now, when you're doing the math on this, you say, okay, how many electrons do we have? Well, oxygen has 6 electrons, and it has 4 halogens. So there's 4 times 7 electrons. That's 28 plus 6 gives me 34 electrons total so far. So how you do it is, the first thing you do is the bonding electrons. This is called electron math. And I use 4 bonds. So 4 times 2 is 8. So I subtract 8 from that, and I get 26 electrons left over. Well, each one of my halogens has 3 lone pairs. So that's 2, 4, 6 times 4 is 24. So I have 2 left over, and that's my lone pair on oxygen. All right? So that's how you do it. You first do the bonds, then you do the lone pairs on the surrounding the surrounding compounds, and then the remaining electrons go on the central atom. Yeah. Yeah. All seesaws will have one lone pair and 4 bonds. So in order to do that, it has to have 1, 2, 3, 4, 5, 6 electrons, which tells you that it's oxygen's family. Because only oxygen's family has 6 valence electrons. So oxygen's family with 4 bonds. So you might see, SBr4. It might be, SEI4. It might be TeF4. It might be H4Te. Okay? So anything from oxygen's family bonded 4 times. All right, that's seesaw. And that's how you do the geometries. So I'm glad I got to do that. All right, so now the next one is T-shaped. So T-shaped is when you have a halogen, okay, and it's got 3 bonds to other halogens, okay, and a lone pair. Right. No. 2 lone pairs, sorry. So, if you do the electrons, you got chlorine's got 7, fluorine 7, fluorine 7, fluorine 7. So that's 28 total electrons. Well, there's 3 bonds, so 3 times 2 is 6, so minus that is 22. Then 2, 4, 6, 8, 10, 12, 14, 16, 18. So then that takes away the outer ones. Okay, and then you have 4 left, so that's why chlorine has 2 lone pairs on it. All right, so that's going to be T-shaped, and it's going to look like that. All right, but it's going to be a halogen in the middle, and then it's going to be with other halogens or hydrogens. Yeah. Yeah, go ahead. All right, so then the last one is linear, okay? And this one is linear with a noble gas. So if I have like xenon, okay, and it's bonded to, 2 halogens, like Zn or ZeCl2, okay, then you count the electrons. You have 8 plus 7 plus 7, so that's 15 plus 7 is 22, all right? Minus 2 bonds, so minus 4 gives me 18 left, all right, where you have 2, 4, 6, 8, 10, 12, so minus 12, so I have 6 left. And that's going to be 1, 2, 3, 4, 5, 6. All right? So that's going to have 6 on that. It's linear. It's going to be a noble gas and 2 halogens. That's how you're going to be able to tell. All right? And I'm not going to lie to you. Like, how are they going to ask the questions? It's going to be something like, they might say, what is the geometries? And have trigonal bipyramidal, seesaw, T-shaped, linear. And then they just give you chemical formulas, and you got to match it. I mean, years past have been different ways, but they might give you, XeF2. They might give you, BrCl3. They might give you, SBr4, and they might give you PF5. And you'd have to match those geometries to those names. Okay? So that's why I said just practice it. All right? So any question with that? All right, just make sure you can name it. Make sure you know the polarity of them. Now, review real quick. How do I know what the polarity of this is? If it's all the same thing, it's nonpolar. How do I know that? Because there's no lone pairs on the central atom. If there's lone pairs on the central atom, it's polar every time. So like this one right here. You say, well, it's all the same thing around it. It doesn't matter. See the lone pair? Boom, polar. This one right here, it's all the same thing around it. But you see the lone pair? Boom, polar. This one right here, it's actually, see the lone pairs? Polar. Okay? So that's how you tell. If there's lone pairs on the central atoms, it's polar. Okay? Like trigonal pyramidal, polar. Even though it's all the same thing. Bent, same thing, but polar.
So is trigonal bipyramidal nonpolar?
Nonpolar. If it's all the same thing. Now, if I took one of these H's off, and put a BR on there, then it would be polar, okay? Because it would pull differently. All right? So what do we need to know for our test? We need to know how to name chemical compounds. So we have to know how to name ionic compounds. You got to be able to, name binary ones, which are simple group 1 or 2 metals plus nonmetals. You got to do transition metals plus nonmetals, group 1 and 2 or transition metals with polyatomics. And then you have to be able to name covalent molecules, right? Remember we use the prefixes, the mono, di, tri, all that. So it's prefix, name of the element, prefix, name of the element, change to IDE. All right, and the Roman numerals for the only goes to ionics. And you do not use any prefixes on ionics. You only use prefixes on moleculars, and that's if you know it's a molecular because the one on the left is a nonmetal, so not 2 nonmetals. And then the last thing is metal properties. What are metal properties? We said metal bonding is a sea of electrons, okay, which describe delocalized electrons. So if I have like copper and zinc, there's just these electrons just floating around, okay, everywhere. They call that delocalized electrons because they're just floating around, and that accounts for the properties of metals. Malleability, which means you can hammer into a thin sheet. Ductility, which means you can roll it into a wire. Good conductors of heat and electricity, high melting points, low boiling points, and they have luster, which means they're shiny. Okay, they have high tensile strength, which means they're hard to break. All right, so those are the properties of metals, and those are determined by the electrons and metallic bonding. All right, so there you go. That's your test review.